Well, hello, my lovely first hour. Good morning to you. Sorry I couldn't be here with you today. We're going to talk about some 2.4 stuff just to finish off these notes. As a reminder, your LTA 2.2 and 2.3 is tomorrow. Please look over those notes and be familiar with those concepts. Also, you're going to work on your lab today. That is going to be due on Wednesday so that you can focus on studying tonight. Here we go, 2.4. This is just a reminder. You shouldn't need to write this down. You should already know it, but I want to mention it. It sets up our notes today well. So it says if no equations are provided for you, you can always use the molar enthalpy of formation of each compound in the reaction to find the overall change in enthalpy. And we've been doing that. So in other words, if you don't know delta H of your reaction and you need to, if you are not given those equations underneath, you guys are now familiar with writing out those heats of formation equations and then rearranging them the way that they need to be rearranged so that you can come up with this value. You guys have been doing excellent at that. What I want to show you today is an easier way to do that. So I'm going to say using heats of formation, but easier. So in other words, using this little table that tells us all the heats of formation values, but even easier than writing your own equations and arranging them. And this is called the summation equation. And the summation equation looks like this. It says that the delta H of your reaction is going to be equal to, this is a sigma, Greek letter, it stands for sum. So it's going to be the sum of all the heats of formation of your products minus the sum of all the heats of formation of your reactants. Okay? So that's the equation. Sum isn't written there. And we're going to apply it and show you just how easy this is. So let's take an equation like this. I've got H2S gas plus fluorine gas, and that's going to make hydrofluoric acid in the gaseous form and sulfur hexafluoride in the gaseous form. And I would like to know delta H of this reaction. So according to the summation equation, if I have my table of delta H values of formation, and there's one on here for all the compounds, I can do this easily. So my delta H of this reaction is going to take into account the delta H of formation for my products and my delta H of formation for my reactants. And before I can do that, just want to make sure that this sucker is balanced, which is clearly not, just by what I'm looking at here. So I'm going to need a 2 there and a 4 there. So if you guys wanted to do this without the summation equation, you guys would know exactly what to do. You take this first compound, H2S, and you write from its elements how you would make 1 mole of that, and you'd look on your table and you'd find your delta H of formation for that guy. And you do the same, not for F2 because it's an element, but you do the same thing for HF, you do the same thing for SF6, and then you go back and you say, all right, this guy got to get turned around, this guy's got to get multiplied by 2, etc. So you're fine with that, and I love that you're fine with that. But let me show you how this is even easier now. So this H2S is a reactant. So I want products, which means I'm sticking over here to this side. So some of my products, I'm going to put it in brackets. My delta H of F for HF, if I look on my table, what I'm seeing is negative 276 kilojoules per mole. And then just like you used to fix it in your equation, there are 2 moles indicated in this expression. So we're going to multiply that by 2 so we can express the number of moles that were actually made. So we're not just making 1, we're making 2. So then we're going to add to that, it's a sum of 1 SF6, and if I look at my table, I'm finding that that's negative 1220. And that's just times 1, so I'm okay. And that takes care of this portion of my summation equation. or excuse me, these are products, this part of my summation equation. Now we're going to do this guy right here, our reactants, which are over on the left-hand side. So we're going to subtract the sum of H2S, and there's only one of those. So I'm seeing that that is a negative 21. So again, 1 times a negative 21 kilojoules. And then my F2 is an element, so there is no value for that. It's just 0. So you could put plus 0, or you could just be done. And that's it. So now I add up the sums and subtract my reactants from my products, and I get my answer. And for this particular reaction, what I'm coming up with is negative 1745 kilojoules. Okay. So if I have that table, this is much easier than writing out all those equations, changing them around, adding them all up. You just got to plug them in, subtract reactants from products. Before you get too mad at me about how easy this is, and I should have just told you this at the beginning, and blah, 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 like I know you're either saying or thinking, I want to just tell you where this comes from, because I feel like that's more important than just plugging the numbers in. So I have kind of a silly little example here for you, and that is taking a snowman compound and breaking it into Mickey Mouse compound plus tower compound. So if I wanted to know the delta H of that reaction, here's what I would have to do. Think of it this way. If this snowman represents a compound made up of each shape is an atom, so 1, 2, 3, the caret is 4, this rectangle is 5, this rectangle is 6, so 6 atoms. In order to make a Mickey Mouse and a tower out of these same atoms, what I would need to do is first completely disassemble the snowman into his component pieces. So if I completely disassemble the snowman into his elements, what that sounds like to me is that this is a heat of formation, but opposite. So heat of formation would be this way, where I took all the snowman's pieces and I put them together and made him into a snowman. So what I'm actually doing in this reaction is not putting them together, but I'm taking them apart. So it's the opposite of the delta H of formation for my snowman. So I'm going to put a negative sign. It's the same process, it's just backwards. So I have my negative delta H of formation of my snowman. Then, to make a Mickey Mouse and a tower, what I would do is put those pieces back together just in a different way. So Mickey Mouse, there we go, and tower, there we go. So what this looks like to me is the delta H here. I'm going to be putting together delta H of formation for Mickey Mouse, which I'll just do MM, and the delta H of formation of my tower. So this was the negative delta H of formation of my snowman. These are positive delta H's because I'm putting together the pieces that came from that snowman in a new way. Now please remember that we said that delta H value is independent of the path. It was like me running errands. It didn't matter if on the way to Myers I went to the drugstore and the gas station and the bank or wherever I went and then ended up here. What matters is that I started here and ended here. So same thing for chemical reactions. It doesn't matter that we pull them apart first and then put them back together. We went from starting with the snowman and ending with Mickey Mouse plus the tower. So what we can do is use these equations to come up with the delta H of the reaction. And one thing I want you guys to notice is if you did this, if you put together the snowman, like if you did 3 white plus 1 orange plus 2 black makes snowman, and you had the delta H value for him, and let's say it was 4. Wouldn't you be looking at that and saying, oh, snowman's a reactant though, so I'm going to turn that around and make this the opposite in sign? That's exactly what you're doing here. The negative delta H, you're just flipping it around. So in your summation equation, if you were going to do the delta H of the reaction, you do the products. If you were to add all of these up together, you'd have the positive delta H's, and then you'd be having negative delta H for your snowman, just like you guys know you would do if you wrote the equation yourself. So that's why for your products, it's positive. So that's why your delta H of your products comes first, because it's positive, because those delta H values should be exactly the way that they're written in your table. But then you're going to subtract the delta H of your reactants, because this negative is a built-in flipping of the sign on your table. So that negative, that subtraction, is automatically making the delta H value on your table opposite in sign like it should be. So that's where this comes from. It comes from ripping it apart. That's the negative delta H of formation. So the negative delta H of formation is ripping it apart, and putting it back together, that's the positive delta H of formation. So that's where it comes from. I wanted you guys to see that. So today you're going to try a few of these with the summation equation only. One thing that I wanted to mention is that if your professor gives you, if he gives you an equation, blah, 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 and then he gives you 3 equations to find delta H, you should not use the summation equation. He wants you or she wants you to use these equations to multiply by 2 or change the sign. That's what they want to see. So don't use the summation equation if you're given equations. But if you're not, if all you're given is just this and asked to find delta H of your reaction, go right ahead and use your summation equation. Or if you're just not comfortable with that, you can write all of your formation equations out like we've been doing, and then do your flipping and multiplying and adding all up. It's totally up to you, but I do want you to try a few of those summation equations today. So without further ado, I will let you have at it. Please remember, labs are not going to be due until Wednesday, even though you are working on them today. So if you don't finish, give them to me on Wednesday. But you do have that big LTA tomorrow, so make sure you study, study, study. Okay, I love you. Bye-bye.